Welcome back for another wonderful day in physics. Today we're working on chapter 11. Up to this point in time, we've looked at constant forces over relatively long periods of time. In this chapter, we're going to look at events where we have a variable force that happens over a short period of time. We're going to talk about collisions and explosions. Okay? A collision is a short duration interaction where two objects collide, okay, or where one object hits another. It's a short duration interaction, and the force over the course of the interaction is variable. Our other type of event we're going to look at in this chapter is an explosion. It's another short-term interaction where the two objects are close together initially and they push apart. And as they push apart, the force that they apply on each other decreases. Now, no matter which type of short-term interaction we're looking at, we see forces as a function of time that are changing. So let's look at a graph. Here's a graph of a collision event, like a baseball being hit by a bat. So we can talk about the compression, where they start to make contact and they get to their fullest contact. Okay, this is coming together, and then this is as they're moving apart, the expansion. The baseball in this short duration time span between beginning of contact and end of contact actually changes shape. It compresses and it expands back out. That's why it says it's labeled a compression and expansion. Okay? The area under this curve is going to be important to us. So we've got force over a duration of time. Now, since force is changing with time, acceleration is changing with time. And this would make, Newton's laws, first law, second law, third law, pretty hard for us to use directly because they're really based on constant forces. So we're going to have to take a slightly different approach, and really we're going to be working at this from Newton's original approach. Because remember, Newton didn't have the kind of equipment that we have, and Newton started looking at things from before an event to after the event, and he really worked with average forces. Now, the force involved in these kind of events is called an impulse force. It's a variable force over a short period of time with a large maximum. So the force starts out low, it goes very high, and it comes down low again. Okay, so during a collision, like we saw in that graph, the force grows with contact and decreases as the object separates. You can think about in an explosion, it starts out with a very, very large force and it decreases as the objects separate. An impulse force is going to cause an acceleration and therefore a change in velocity. So if we can observe changes in velocity, we can learn something about average acceleration and we can learn something about average impulse force. So we're going to talk about momentum. The symbol for momentum is P. Momentum, like velocity, is a vector quantity. And it's the velocity of an object multiplied by its mass. So momentum, P, is equal to m times v. So remember that momentum is a vector quantity, which means it could have x and y components, okay? And change in momentum, then, is going to be associated with the application of a force. Because we know to cause an acceleration, we have to apply a force, And when we have an acceleration, we have a change in velocity. Okay? Now, let's kind of play the math game and connect the dots. When we apply a force to an object, it causes a change in momentum for the object. If the mass is constant, then force, as Newton saw it, is a change in momentum with time. So momentum is mv. So if mass is constant, okay, we get m dv dt. dv dt is acceleration, so force equals mass times acceleration. That's how Newton worked it out. So in this chapter, we're going to concentrate about thinking of force as the rate of change in momentum with time. Okay? So force can be thought of as the rate of change in momentum with time as easily as the rate of change of velocity times mass. Okay? Now, an impulse, J, is change in momentum. Okay? And it's related to the average force applied for the time of application. If we were to look at a graph of force versus time, the impulse, J, would be the area under the graph for the time of the variable force application. So we can say that J, the impulse, change in momentum, is the average force times the duration of the collision, or it's the area under the curve. The average force applied, then, is commonly referred to as the average impulse force. And we can say that momentum final is going to equal momentum initial plus the impulse. So we're going to look at some really simple problems. Okay, we're going to look at problem 1, 2, 3, and 10. So let me get the book all set up here, and we will look at these problems. Okay, over to the document cam. Let's scoot this way up. Okay, if we look at problem 1, it says, at what speed do a bicycle and its rider with a combined mass of 100 kilograms have the same momentum as a 1,500 kilogram car traveling at 5 meters per second? All right. Now, we know that momentum equals mass times velocity. So here we're just going to look at the absolute value of these because it didn't specify direction. Okay? So for the bike, the momentum is going to be the mass of the bike rider and the bike, which is 100 kilograms, and the velocity, we don't know. For the car, okay, the magnitude of the momentum would just be the mass, 1,500 kilograms, times its speed, 5 meters per second. So 5 times 1,500 says the momentum of the car has a magnitude of 7,500 kilograms meters over seconds. So if we look at it for the bike, 7,500 kilograms meters over seconds would equal 100 kilograms times v, the magnitude of v. So the magnitude of the velocity here is 75 meters per second. I don't think I want to be on that bike. But anyway, so that's problem 1. Now, if we look at problem 2, I think that one's probably too simple. So let's look at problem 3. It says one impulse does the force shown in figure 11.3 exert on a 250 gram particle. Okay? So if we look at this problem, we're asked about this graph. And remember, the impulse, the change in momentum, equals the area under the graph. So if we look at the impulse here, think about the first 4 seconds and then the last 6 seconds. In the first 4 seconds, I've got a triangular shape. So I can get the area under there as 1/2 the base times the height. So I'm going to have 1/2 times the base, which is 4 milliseconds. So that's 4 times 10 to the minus 3 seconds. And the height is 1,000 newtons. Okay? And then I'm going to add to that the area of the rectangle, which is 2 times 10 to the minus 3 seconds times 1,000 newtons. Okay, guys? So I've started writing this out. So go for the area under the graph, 1/2 the base times the height. Now remember, a newton is a kilogram meter over second squared. If I multiply that by a second, I get a kilogram meter over second, which is the units for momentum. So let's start multiplying this through. Excuse me. 4 exp3 negative times 1,000 divided by 2. So I've got 2 kilograms meters over seconds plus 2 exp3 negative times 1,000, 2 kilograms meters over seconds. So I've got 4 kilograms meters over seconds. Your book always works everything to 3 sig figs. So that's what the impulse would be, the change in momentum. Okay? Now lastly, before we move on, we're going to look at problem 10. Okay? So let's slide over here again. And we're going to look at problem 10. It says a sled slides along a horizontal surface on which the coefficient of kinetic friction is 0.25. Its velocity at point A is 8 meters per second. Its velocity at point B is 5 meters per second. Use the momentum principle to find how long the sled takes to travel from point A to point B. Okay? All right, now, the momentum principle says that P final has to equal P initial plus J, the change in momentum, okay? And we know that P initial is going to be the mass of the sled times its initial velocity, which was 8 meters per second. Its momentum final is going to be the mass times 5 meters per second. Okay? So m times 5 meters per second has to equal m times 8 meters per second plus j. Okay? So if I look at this, I'm going to get j is equal to m times a minus 3 meters per second. That's the change in momentum. And we know that force equals essentially change in momentum with time. Okay? So far so good. Everybody with me? And we can say that that has to equal the mass times the acceleration. Now, the force here has to be mu times, well, I'm going to leave it like that. It has to be equal to mu times m times 9.80 meters per second squared. Because if you think about it, normal force, force due to gravity, frictional force. Okay? So our frictional force, if we start combining things, I've got 0.25 times the mass times 9.80 meters per second squared has to be the change in momentum, m times a minus 3 meters per second, all over delta t. Okay? So, I can notice that the mass and mass divides out, and if I solve for delta t, I get minus 3 meters per second divided by 0.25 times 9.80 meters per second squared. So 3 divided by 0.25 divided by 9.8. Our time is 1.22 seconds. Now, the question asks us, find how long the sled takes to travel from part A to part B, and that's exactly what we did. Okay? So, we use the fact that we know how to calculate friction. So we know here the magnitude of the normal force equal the magnitude of the force due to gravity, which would just be mg, and the frictional force would be mu mg here. Okay, and that's how we got that. Now we're ready to move on to the next step. In this chapter, just like the last two chapters, we can talk about a conservation law. A conservation law is something that says that something is conserved. Okay? So in this case, we're going to be talking about the law of conservation of momentum. The law of conservation of momentum says that in an isolated system, the total momentum for the system is constant. As long as we have interactions inside the system, the momentum of individual objects could change, but the total momentum of the system will stay the same. So if we choose our system carefully and we look at the instant right before an event, like a collision, and right after the event of the collision, then momentum initially has to equal momentum final. In an explosion, if we look at the instant right before the explosion and right after the explosion, again, we have conservation momentum, and momentum initially is going to equal momentum final. Okay? So when we talk about collisions where two or more objects bump into each other and interact for a short term, they can either be inelastic collisions or elastic collisions. Okay? In an inelastic collision, the objects stick together and are attached after the collision. In an inelastic collision, momentum is conserved. In an elastic collision, the objects recoil off each other, okay? And we'll talk more about that later because there's some extra kind of layers of things we have to add in for an elastic collision. Right now we're looking at inelastic collision. Now, remember we have to make good choices about what's in our system to apply this law, and we're going to look at the moment right before collision and the moment right after collision. And we're going to start off by looking at one-dimensional collision problems. Just because it's easier. Okay? All right, now, first problem we're going to look at is problem 14. Okay? All right. Down. And there. Okay, it says a 5,000 kilogram open train is rolling on frictionless rails at 22 meters per second when it starts pouring rain. A few minutes later, the car's speed is 20 meters per second. What mass of water has collected in the car? Okay? So, if we look at before, I've got my car here. It has a mass of 5,000 kilograms, and it's got a velocity initially of 22 meters per second. After, it's got a mass of 5,000 kilograms plus m for the rain, okay? And it's traveling now at 20 meters per second. So the momentum initially is going to be 5,000 kilograms times 22.0 meters per second. Momentum final is going to be 5,000 kilograms plus m times 20 meters per second. And they have to equal each other. So 5,000 times 22. So I've got 1.10 times 10 to the 5 kilograms meters over seconds has to equal 5,000 kilograms plus m times 20 meters per second. Divide through by the 20. So I have 5,500 kilograms equals 5,000 kilograms plus m. So m has to be 500 kilograms. So that car that was open collected 500 kilograms of water in just a few minutes. Okay? Now let's look at problem 18. Guys, this is one of my favorite problems for this chapter. Okay? We look at problem 18. A 300-gram bird flying along at 6 meters per second sees a 10-gram bird heading straight towards it at a speed of 30 meters per second. The bird opens its mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing? Let's look. Okay? So, again, in this chapter, it's all about thinking about before and after the event. So if I think about the before, I've got my bird, whee, pretty tail, wings flapping, little bitty mouth open, flying along here, okay? And its velocity initially is going to be in this direction. So the momentum initially here of the bird, it's a 300-gram bird, so 0.300 kilograms, times the speed, and the way I have it drawn, this is going to be plus 6 meters per second, okay? So it has a momentum initially of 0.3 times 6, so 1.80 kilograms meters over seconds. And here's my bug. Okay, so my bug's kind of out of size, you know, but his wings are flapping. He's flying in this direction. Momentum initially for the bug is going to be its mass, which is 10 grams, so 0.010 kilograms, times its speed, which is 30 meters per second, but he's flying in the opposite direction, so that's going to be negative. So 30 times 0.01 gives me 0.300 kilograms meters over seconds. Okay? In the after, I have a very happy bird. Mouth closed now because he's got his bug, and the little bug's inside. It's going to have a V final. Now I have a new mass of 0.310 kilograms because the bug is inside the bird. This is an inelastic collision. They're together. Momentum final here is going to be 0.310 kilograms times V final. So if I say momentum, and sum of the momentums initially has to equal sum of the momentums final, I have 1.80 kilograms meters over seconds plus a minus 0.30 kilograms meters over seconds has to equal 0.310 kilograms V final. So 1.8 minus 0.3 divided by 0.310 says that V final for the bird, where are you? Sorry guys, I had to take Mike's call. It was important stuff about classes in the spring. So let's see where we are. We got our before and after. So my bird, 1.8 minus 0.3 divided by 0.310 says that my bird is now traveling at 4.84 meters per second. Well, the bird-bug combo, and it's positive, so the bird's still traveling in its original direction. The bug is now inside the bird going the opposite direction. So notice the bird slowed down when it swallowed the bug. I love that problem. Okay? Now, we're going to look next at problem 41. Okay? So you guys look at that problem. And I'm going to get problem 41 all lined up here. Let's see, problem 41, let's do problem 35 first so that I kind of do them in order. Okay. Oh, that's an explosion. Well, that's okay. All right, let's look at problem 35 here. It says a small rocket with 15 kilonewton thrusts burns 250 kilograms of fuel in 30 seconds. What is the exhaust speed of the hot gases? Ooh, they have changed my problems on me. That's really an explosion problem. We'll look at that one later. Okay, in problem 41, if I look at it here, it's not quite the problem I want either. So let me see if I've got one more. Nice collision problem. Okay, let's look at problem 19. Okay. And then we'll move on. It says a parking brake on a 2,000 kilogram Cadillac has failed and is rolling slowly at 1 mile per hour towards a group of small children. Seeing the situation, you realize you have just enough time to drive your 1,000 kilogram Volkswagen head-on into the Cadillac to save the children. With what speed should you impact the Cadillac to bring it to a halt? Now guys, one of the nice things about these momentum problems is as long as the masses are in the same unit and as long as the velocities are in the same unit, you really don't have to worry about what the units are. So I'm not going to worry about changing miles per hour to meters per second. Okay? Now, if we look at problem 19 here, I have my Cadillac and my smaller car, and the velocity initially of the Cadillac is in this direction. Velocity initially of the small car will have to be in the other direction. And after, they're going to be sitting with a velocity equals 0. Okay? The velocity initially of the Cadillac is a +1 miles per hour. The velocity initially of the small car, we don't know. Okay? The mass of the Caddy is 2,000 kilograms. The mass of the small car is given to us as 1,000. So, I have 2,000 kilograms times a +1 miles per hour plus velocity initially of the small car times 1,000 kilograms, and they're going to be 1 unit, so 3,000 kilograms, and the velocity finally is 0. So if we solve this, 2,000 times 1 divided by 1,000, what I get is velocity initially for the small car is a minus 2 miles per hour. So the Volkswagen has to be going twice the speed of the Cadillac when it hits it head on to stop it. Okay? So let's talk about explosions. Now, an explosion is where particles of system push against each other for a brief instant in time and move away. The really nice thing about explosion problems is that the momentum initially for the system is 0. So the momentum of each object that's pushing against each other, because in the beginning they're sitting still, is 0. It's going to make the math real easy. The two objects that move apart have to have opposite direction momentum. So a gun and a bullet, an arrow and a bow, parts of a bomb, two skaters facing each other and pushing off in the middle of a skating rink. You've heard about the recoil of a gun. The recoil of the gun is related to change in momentum.